Hello students, this is Dr. Ben, and let's work on the last problem that is on the homework for Chapter 4, hand-graded Part 2. And this is problem number 80 in our textbook, and it involves a variation of the Atwood machine that was actually the subject of problem 4.22. And so rather than both of the objects hanging from strings and moving in the vertical direction, we can see in the picture that one of the objects is allowed to move on an incline while the other one is hanging. So I've made a list of what I was told in the problem, and so the hanging mass is going to be labeled by a symbol capital M, and the sliding mass is going to be labeled by a symbol little m, and the plane angle is going to be an angle of theta. Alright, and so in this problem we are asked to find two different things. The first is the tension that's in the string that connects the two objects together, and the second is the time that it takes for the sliding block to move a certain distance down the incline. So the tension is going to be a forces problem. So we'll use Newton's second law, and then the final time is going to be a motion problem, and we can use the acceleration that we find from the first part and the kinematic equations. So we have to solve this problem sequentially, and the incline is rough, that there is a coefficient of friction that is given, and so we have to take into account the frictional force. Alright, so we need to do the forces part of the problem first in order to find the tension, and so the tool that we use to solve the forces part of the problem would be force diagrams. So let's first of all draw a force diagram for the hanging mass. So it would have a downward force caused by gravity that would be capital mg, and an upward force caused by the string that's called tension. And in the numbers that are given, the hanging mass is lighter than the sliding mass, so we're going to draw the direction of the acceleration to be in the upward direction for the hanging mass, and I'll use a coordinate system where the positive y direction is up. Alright, then for the sliding mass that is on an incline, we'll draw its force diagram. So there's the sliding mass, and the dot represents its center. So there are several different forces that act on the sliding mass, as we have learned in Chapter 3. So there's the normal force, and then there is the weight force, and that's going to be labeled little mg. And that weight force makes an angle of theta with the extension of the vertical, which is the same as the plane angle. All right. The velocity of the sliding mass is going to be down, and so that implies that the frictional force is going to be opposite to the direction of the motion, so that will point up the hill, and the tension will also point up the hill because the two tension arrows need to point towards each other. The pulley just changes the direction of that tension. And we also need to have a coordinate system for the sliding mass, and so we're going to use our typical coordinate system where x is down the plane and y is perpendicular to the plane. Okay, so the hanging mass only has vertical motion, but the sliding mass has both horizontal and vertical components of the forces that are given. So when we apply Newton's second law to this system, we have to we'll have three different equations, and I can see that I forgot to indicate the direction of the acceleration of the sliding mass. So if the hanging mass moves up, then the sliding mass moves down the hill. And so now I've got that indicated. All right, so let's do the simpler parts first. So let's start out with the hanging mass, and we'll consider its motion, its forces. So we're going to use Newton's second law to solve for both of the objects. So we'll just write down the textbook version, A equals F net divided by M. And for the hanging mass, then I would have that A sub y is equal to the net force in the y direction divided by the mass. So that would tell me that plus A, which is the size of that acceleration, would be equal to the quantity T minus capital mg divided by capital M. So I'm going to put that equation in a box because I'm going to need it in a little bit. All right, so for the sliding mass, in the y direction, the net force is going to be equal to 0 because there's no motion in the y direction. So that would tell us that, if I move my paper down just a little bit so we can see that whole force diagram, we would have the normal force minus the shadow of the weight in the y direction, which is little mg times the cosine of theta, equals 0. So we can solve that for the normal force. So the normal force would equal mg times the cosine of theta. And that allows me to find the frictional force, which will be equal to mu k times n, which will equal mu k mg cosine of theta. And I'll put that in a box because I'm going to need that when I consider the x motion of the sliding mass. All right, so let's bring our paper back down so we can see the force diagram. So again, to remind ourselves that the weight force has a shadow that points in the x direction, and that's the side that's opposite to the angle. And then we have both the frictional force and the tension force that points up the hill. So for the sliding mass, the net force should have 3 different terms. So we can go ahead and write that down now. So in the x direction, the acceleration is positive, and I'm going to use the same symbol as I used for the hanging mass because the magnitudes have to be the same if they move as a unit. So that will be equal to the shadow of the weight in the x direction, mg sine of theta, minus the tension, minus the frictional force, and that is all divided by the mass. And I'll put that in a green box. Okay, so we have to combine all 3 of these equations together to solve this problem. So we're interested in the tension, so we want to eliminate the acceleration, but we're going to use the equation for the friction that we found from the y direction. So this takes a little bit of effort to solve all this. So we just have to take our time. So we're going to set the acceleration equal to each other. So A is equal to A, and we'll set the first A for the hanging mass equal to the equation for the A for the sliding mass that we found. All right, so I need to have some more workspace here. So that's going to tell me that T minus capital M G over capital M is equal to little mg sine of theta minus t minus the frictional force. And I'll just go ahead and put in the formula for the frictional force that was up above, and that will be equal to mu k little mg times the cosine of theta. And all that is going to be divided by little m. So our goal is to find the value of the tension. So I want to solve this equation for the tension, and I'm going to do that by cross-multiplying and then collecting like terms together. So I'm going to cross-multiply first of all. So that'll give me T times little m minus big M little m g is equal to capital M multiplied by this bracket, little mg sine of theta minus t minus mu k little m cosine of theta. So now I'll multiply out the bracket that I have on the right hand side. So I have t times little m minus big M little mg equals big M little mg sine of theta minus big M t minus mu k big M little m cosine of theta. Alright, so I need to collect terms now. So I need to take the tension term to the left, and I need to take this big M little mg over to the right. So I have t times little m plus t times big M equals big M little mg plus big M little mg sine of theta minus, somewhere I lost a g up here. I lost it right here. Big M little mg times mu k cosine of theta. Alright, so again, we just have to be systematic about our algebra. So I'm going to factor out a t on the left-hand side, little m plus big M. And now we can see on the right-hand side that we have a little m big M g in each of the three terms. So I can factor that out and get 1 plus sine of theta minus mu k times cosine of theta. And then I can do one last step and divide both sides by the bracket that's on the left. So I have big M little mg times the quantity 1 plus sine of theta minus mu k times the cosine of theta, and all that is divided by little m plus big M. So that is the value of the tension, and when you plug all the numbers in to get that numerical value, the tension, I'll do this in red, the tension turns out to be 87.8 newtons. So I'd already worked that out ahead of time, so I had that number. 87.8 newtons is going to be the value of the tension, and so that's the answer that we need for the first part of the problem. So as the crate slides down the incline, what is the tension that's in the rope? So to do the motion part, which is part B of the problem, I need to know what the acceleration is of each of the objects it's the same value. They move as a unit, but just in different directions. So I need to use this tension in order to find the acceleration. And so if we go way back up further, the easiest way to find the acceleration is to use the equation that we had developed for the hanging mass, because we see that we can find the acceleration directly from the tension and the weight of the hanging mass. So just kind of put that in your memory. A equals T minus mg over m. So we'll go back down here and we'll write that A equals T minus capital Mg over capital M. And if we plug the numbers into that expression, we get that the acceleration is 1.17 meters per second squared. And so we're going to need that acceleration to do the kinematics for the second part of the problem. All right, so this problem's kind of long, so we need to go back and read what the second part says. How long does it take for the crate to slide 2 meters down the incline? All right, so to do a motion problem, we need to draw a pictorial representation, and we're interested in the motion of the sliding block, so we're going to draw a pictorial representation on a ramp, on an incline. So I'll need 2 different points of interest, an initial point and a final point. And we'll put the origin at the initial point, and we'll call the positive x direction down, and the value of the acceleration we just found, which is equal to 1.17 meters per second squared. And I have the kinematic variables xi, vi, t sub I, and xf, vf, t sub f. So this actually looks very familiar. It's the same geometry that we had in problem 4.24 that we just did. So my table of knowns for the sliding mass would be xi is equal to 0, vi is equal to 0, ti is equal to 0, xf is equal to 2.0 meters. We're told that's how far the object moves, and we want to find the value of t sub f. So we have to figure out which of the kinematic equations to use. We want to find the time. So, and we know something about the position, so it would make sense to use the first kinematic equation. They would say x final equals x original plus v original t final minus t original plus 1/2 a times t final minus t original squared. And we'll cancel out the symbols that are equal to 0 before we do any algebra. So the initial position is 0. The initial velocity of the sliding block is 0, so the whole second term goes away, and the initial time is equal to 0. So we can see that our equation looks much simpler, that xf equals 1/2 a times t sub f squared, and if I solve that for t sub f, I would have 2 times xf divided by a equals t sub f squared, and then if I take the square root of both sides, t sub f would be equal to plus or minus the square root of 2xf divided by a. And when I plug in the numbers, I keep the positive root because time can't be negative, and I get 1.85 seconds. All right, so let's recap for a second. In part A of the problem, we used the forces to find the tension. And while I was at it, I went and found the acceleration of the objects because I needed that for part B of the problem that was about the motion. So we used the motion ideas, the kinematic equations, to find the value of T sub F. So the forces in Newton's second law helped us find the tension, and the tension and the acceleration we used in the motion part of the problem in order to find the time. All right, so there you have it. Problem 4.80 from the second part of the homework for Chapter 4.